Director of Nuclear Polytechnic, Dr. Zainal Arif, Director of Talent Management, Dr. Ajeng Arumsari, from Rosatom Russia, Mrs. Anna Bilbaneva, from the Russian House in Indonesia, the Director of the Russian House in Indonesia, Mr. Nikita Silikov, from Tomsk Polytechnic University, Dr. Vera Verhoturova, the speakers, the juries of Global HACKATOM Indonesia 2025, and all of the participants of today's event. Welcome to the Global HACKATOM Indonesia 2025, which is held in collaboration with BRIN's Nuclear Young Talent Fest 2025. We are so glad to have you here today. My name is Indah, and I'll be with you throughout today's event. This event is held as a collaboration between BRIN's, Tomsk Polytechnic University, and Rosatom Russia. Besides being held here in Nuclear Polytechnic, it is also live in YouTube BRIN Indonesia. And gentlemen, first of all, before we begin, let us all sing the Indonesian national anthem, Indonesia Raya, and I kindly request all of you to stand up. Thank you. Please be seated. Ladies and gentlemen, for this morning agenda, we will have several lectures regarding nuclear technology, application, and study, as well as BRIN's talent management program, which can be a good opportunity for all of you to strengthen your capabilities in research and innovation agency through various fields of study, including in the field of nuclear area. But before we get to the main agenda, allow me to invite the Director of Nuclear Polytechnic, Dr. Zainal Arif, to give his welcoming speech. Please, Dr. Arif, the session is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. A very good morning, dobre utro, peace and greeting to all of you. Yang terhormat Deputi Sumber Daya Manusia IPTEK BRIN, distinguished guests, distinguished delegates from Thomas Polytechnic University and from Rosatom, and also distinguished speakers for this event, and respected colleagues from BRIN, and honored guests, and also director of Russian hosts in Indonesia, esteemed faculty members, and dear participants and students. It is a great privilege and honor for us, Polytechnic Nuclear Indonesia, or Polytechnic Institute of Nuclear Technology Indonesia, as part of BRIN, to welcome all of you in this event, Nuclear Young Talent Festival 2025. Right here in this Polytechnic, in this city, Yogyakarta, the culture city in Indonesia. This festival is more than just academic gathering. It's a living testimony to international collaborations and also to share commitment, idea, and concept, and also creativity among us concerning about the development of nuclear technology. And likewise, we extend our deepest appreciations to Deputy for Human Resources of Science and Technology BRIN, whose leadership in developing a strong and future-ready scientific workforce continues to inspire and empower institutions like ours here. To our students and participants, this festival is designed with you in mind. You are the future of Indonesia's nuclear capability, not only as engineers and scientists, but as innovators, communicators, and also leaders. And let this moment where your curiosity grows into convictions and your ideas find the directions. Through the competitions, exhibitions, and knowledge sharing sessions, we hope you will gain insight and build networks and realize that you are part of something bigger, as part of national agenda about the development of nuclear technology in Indonesia. Let me close by thanks all partners, especially from TPU and from Rosatom, for their support and collaborations with BRIN, especially with Poltech Nuclear here. And may this event be start of many more collaborations programs and joint efforts to empower young nuclear talents in Indonesia. Once again, welcome to Nuclear Young Talent Festival 2025. Let us work together, let us learn together, let us connect together, and let us grow together. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. Spasiba.
Thank you, Dr. Zainal. Next, I would like to invite Mrs. Anna Bilkeneva to give her welcoming remarks. The session is yours.
Selamat pagi, dear friends, dear students, distinguished organizers, Dr. Zainal, Dr. Edi. My name is Anna. I represent Rosatom State Corporation from Russia, and it's an honor for me today to be here. I would like to say thank you for BRIN and for Polytech Nuclear for organizing and hosting this event today, and for having so many bright students in this audience. it's an honor for me to speak to future, I hope, nuclear scientists, experts in radiation technologies, engineers, designers, and people who will develop national nuclear program of Indonesia. This year, Rosatom celebrates 80th anniversary of Russian nuclear industry. And we have a big experience both in nuclear energy technologies and in radiation technologies, which can help to increase the quality of people's life in different spheres, in medicine, in agriculture, to develop science. And what is very important, all these technologies, they require a lot of knowledgeable experts and specialists. And I hope very much that we will develop our cooperation with Indonesia in this sphere, in developing education, developing knowledge in the sphere of nuclear technologies, to make people's life better in different spheres. So I wish you all good luck, and I hope very much to see you some days, at least the winning team in Russia for our international competition. But you all, yes, you all are welcome on different programs and projects for students, which we develop together with BRIN and which we develop internationally. You are welcome to participate in all our events, which are dedicated to nuclear technologies and radiation technologies. Terima kasih banyak. Thank you and good luck once again.
Thank you, Mrs. Anna. For next, I would like to invite the Director of Russian House in Indonesia, Mr. Nikita Silikov, to kindly give his remarks, please. The session is yours.
Okay, so dear HACKATOM participants, estimated partners from BRIN and Poltech Nuclear, ladies and gentlemen, it's true honor for me to welcome you today at the first ever HACKATOM in Indonesia, an event that symbolizes the spirit of innovation, friendship, and peaceful progress. This year, Russia celebrates 80 years of its nuclear industry, an industry that has not only powered our cities, but also saved lives through nuclear medicine, preserved the environment, and expanded knowledge. We are proud that Indonesia joins the global movement today. Exactly 1 month ago, we witnessed an important moment. President of Indonesia, Prabowo Subianto, visited Russia, underlying the strong and growing ties between our two countries. Russia and Indonesia share a common vision, a peaceful, multipolar world where technology serves people. Today, in this room, we see the spirit of Golden Indonesia 2045, a generation of future leaders, engineers, and innovators who will shape the future of your great nation. The fact that this hackathon is dedicated to the theme nuclear technologies for health and life shows exactly what kind of future both Russia and Indonesia believe in, one that is smart, responsible, and human-centered. As a Russian house, we believe in people-to-people diplomacy, in connecting young talents, researchers, and thinkers. HACKATOM is a shining example of that. To all participants, be bold, be creative, and be responsible. Your ideas can heal, protect, and inspire. We look forward to seeing the winning team in Moscow this fall for the global final. And also, I would like to mention, so don't hesitate to contact our office in order to get a scholarship for education in Russia. All of you are welcome, and we will do our best to help you to choose the best university that will suit you well. Thank you very much. Спасибо. Terima kasih.
Spasiba. Thank you, Mr. Nikita. And lastly, please, Dr. Vera Verkhoturova from Tomsk Polytechnic University to give us a welcoming remarks as well. The session is yours.
Very good morning, ladies and gentlemen, dear Dr. Zainal, dear Dr. Eddie Giri, dear colleagues from Rosatom, dear students, because you are the main guests of today's events. So thank you very much for being with us today. And on behalf of Russian delegation, I would like to say our thank you to our friends from Poltech Nuclear for hosting this event today, and for our friends from BRIN. And I would like to say thank you to Dr. Eddie Giri for the support from BRIN of this unique event, because, dear students, today you are the participants of the unique national event. This is the first national nuclear students competition in Indonesia, and you are the finalists of this competition. It means that you are already the best in nuclear in your country. So the project, which is named HACKATOM, is unique project of Rosatom, Russian nuclear corporation, because it has already been organized during the last 3 years in more than 12 countries. And it has about 1,000 participants from all around the world. And this year, this is the first such competition in Indonesia, which means that you are already the members of this nuclear young professionals club. And I would like to congratulate all of the students today with this achievement. So moreover, the uniqueness of this event this year is that this event is connected to the 80 years anniversary of Russian nuclear industry. And that's why Russia and Rosatom gives a unique present for every winning team in every country. The team who will take the first place tomorrow will get a unique opportunity to come to Russia in September with the support of Rosatom and to participate in the international HACKATOM competition. And this team will present all the country in this national competition. There will be just one team from any country. And the team who will be the winner tomorrow, you will be the ambassador of your country in young nuclear competition in Moscow in autumn, which is dedicated to the 80 years anniversary of Russian nuclear industry. And I would like to say that nuclear, that is the reason that all of us are here today, is very prospective and very promising technological direction for any country. It will be presented today by the experts of our university. Nuclear is not only about energy. Nuclear is about health, because you can't fight with cancer without using nuclear technologies. Nuclear saves our lives. Nuclear provides the food security for any country. Nuclear helps us to develop higher current semiconductors, which is the heart for many industrial applications. So we can say that nowadays nuclear technologies is the issue of survival for any country that would like to be the leading technological country in the world. And I would like to wish you to make your input as the young professionals in the future nuclear technological development of your country, and to assure the technological prosperity of your country in nuclear and nuclear-related areas. And I wish all of you good luck for today and for tomorrow. Thank you very much.
Thank you, Dr. Vera. And now, ladies and gentlemen, we will begin the main agenda, the lectures from our distinguished speakers. Allow me to invite Dr. Mikhail Anikin, Head of Nuclear and Radiation Safety, Department of Nuclear Research Facility of Tongs Polytechnic University, Dr. Artem Naimushin, Director of Nuclear Research Facility of Tongs Polytechnic University, and also Bapak Edi Giri Rahman Putra, Deputy for Human Resources of Science and Technology BRIN. Please come to the stage. Please come to the stage for all our speakers. And we will also later have Miss Vera Upirova from Project Office for Education Development and International. Please be seated. Later, we will also have Miss Vera Upirova from Project Office for Education Development and International Cooperation Rosatom State Corporation by online, and also Mrs. Naba Adilafat, Ambassador of the Russian Nuclear Education, who will also join us online. Please be seated for all of our speakers, Dr. Mikhail Anikin and Dr. Artem. Okay, and for this session, let me also invite Professor Dr. Julwan Henry Purba, one of the jury for the Global HACKATOM Indonesia 2025, who will be the moderator of this session. Please come to the stage. And for this session, I will give the moment for Dr. Julwan.
Thank you very much. Good morning, everybody. Selamat pagi adik-adik mahasiswa. This is a good time for us, especially for you, to wider or to emphasize your knowledge about nuclear technology development, especially in Russia through Tomsk Polytechnic University. So please use this time to ask questions as many as you have. So it will be able to enrich your paper for tomorrow's session, right? And this panel, we have 5 panelists actually with 6 topics. And 2 of them will join us through Zoom. And because of time differences, they will join us at 11 o'clock. Okay, so let me introduce the panelists here in front of us. The first one is Dr. Mikhail Anikin. He will present power application of nuclear technologies, current status, and the prospects of the development. He is the head of Nuclear and Radiation Safety, Department of Nuclear Research Facility of TPU. And the second speaker will be Dr. Artem Naimushin. He is a director of Nuclear Research Facility of TPU. And the third speaker, back to Mikhail Anikin with the second topic, right? So you have 2 topics in this panel, only one. Or the bigger one. So you combine in one session. Okay, good. Thank you. And then we'll make a break. Without break. We break. Okay, we'll break. Okay, then from Pak Edi Giri, he will present nuclear young talent programs in BRIN, and then followed by 2 panelists from Zoom, which are Miss Vera Upirova, Project Office for Education Development and International Cooperation, Rosatom State Corporation. She will present study nuclear technology in Russia. This is a good time for you to know how to study, what the interest point of studying in Russia. And then the last one is Miss Naba Adilafat, ambassador of the Russian nuclear education. And the topic of her presentation will be sharing a session about experience of education in Russia. So let's have this time to enrich your knowledge about nuclear technology development. And please give big welcome to the first presenter, Dr. Mikhail Anikin.
Hello. Good morning, dear colleagues. So my name is Mikhail Anikin, and I'm from Tomsk Polytechnic University. And now, could you? My presentation today will be about non-energy purposes of nuclear technology. And it will be divided by two parts with a short break. The next slide, please. Next. Okay. So, nuclear technologies are directly related to nuclear reactors. So at the beginning, it's need to tell what is nuclear reactor is. A nuclear reactor is a device used to initiate and control the fission nuclear chain reaction. Fissile nuclei, primarily it's uranium-235 or plutonium-239, absorb the single neutron and split, releasing the energy. And the next, it's multiplying neutrons, then can induct further fission. In nuclear reactors, these processes are stabilized and under constant control. On December 1942, the first human-made chain reaction was initiated in the first artificial nuclear reactor, Chicago Pile. Chicago Pile during the experiment led by Enrico Fermi. On December 1946, the first nuclear reactor in Europe was started to operate in Kurchatov Institute in Moscow. And in June of 1954, the first nuclear power plant in the world was built and started to operate in the Obninsk in Soviet Union. Next slide, please. So the main components of each reactor, despite of its type, its project. So its reactor consists of very important elements, such as reactor core with the nuclear fuel, neutron reflector that surrounding the reactor core, coolant for removing released energy, chain reaction control system, including emergency protection, of course, radiation protection system, and remote control system. All nuclear reactors can be classified by its purpose. First of all, power reactors designed for produce electrical and thermal energy used in power engineering. Such reactors are mainly used in nuclear power plants. The thermal capacity of modern power plants reach 5 gigawatts. Transport reactors designed for supply energy to vehicle engines. The most widely used groups are marine transport reactors used on submarines and various surface vessels, as well as the reactor used in space technology. Experimental reactors designed to study various physical quantities, the value of which is necessary to design and operation of nuclear reactors. The capacity of such reactors does not exceed several kilowatts. Research reactors in which the neutron and gamma fluxes created in the reactor core are used for different research in the field of nuclear physics, solid states physics, radiation chemistry, biology for testing materials intended to operation in intense neutron fluxes and for the production of isotopes. The capacity of research reactors does not exceed 100 megawatts. The released energy usually not used. And the industrial reactors used to produce isotopes used in various fields. They are mostly widely used to the production of nuclear weapons materials, for example, plutonium-239, and also reactors used for desalination of seawater are also classified as industrial reactors. Reactors are often used to solve two or more different problems, in which case they are called multi-purpose. For example, some power reactors, especially at the dawn of the nuclear power, were intended mainly for experiments. Fast neutron reactors can simultaneously produce energy and isotopes. Industrial reactors, in addition to their main task, often produce electrical or thermal energy. But not all nuclear reactors are human-made. Nature also can build its own reactor. The natural reactor in Oklo formed where the uranium-rich mineral deposit get contact with groundwater, which could act as a moderator for neutrons. A chain reaction took place, producing heat, and that caused the groundwater to boil away. Without water, the reaction slowed and stopped. When the cooling of mineral deposit, the water returned and the reaction restarted, completing a full cycle every 3 hours. The fission reaction cycle continued for hundreds of thousands of years and ended when the decreasing of fissile materials coupled with the build-up of neutron poisoners no longer could sustain a chain reaction. The concentration of xenon isotopes found trapped in mineral formation 2 billion years later make it possible to calculate that the specific time intervals of reactor operation, approximately 30 minutes of criticality, followed by 2 hours and 30 minutes of cooling down to complete a 3-hour cycle. So let's return in nuclear installations that are intended for performing experiments. What is the research nuclear facility? Is the nuclear facility that includes a research reactor or critical assembly or subcritical assembly with a complex of structures, systems, experimental devices, and necessary personnel, and intended to produce and use neutrons and ionizing radiation for research and other purposes specified by this project. And now we need to classify the research reactors. First of all, its purpose is physical research reactors. As a rule, targets and experiments are located behind the biological shielding in the path of neutron and gamma radiation beams. These beams are formed by channels that penetrate the thickness of biological shielding and reflector in various directions. Material science reactors are used to study of reactor materials, structural, coolants, moderators, and so on, in intense fields of neutron and gamma radiation to test the resistance of radiochemical elements and units to conduct fundamental and applied research in radiation chemistry to study the effect of radiation of synthetic materials. Typical experimental devices in these reactors are experimental loops. A loop is an autonomous coolant circuit for experimental channel built into the reactor core to maintain the required test mode. For example, temperature or specified coolant. They can simultaneously irradiate fuel elements of completely different design for water, boiling, gas-cooled reactor, and other reactor system. A reactor for production of nuclides are characterized by high neutron flux density, which determines the rate of their formation and accumulation. Reactors for production of nuclides are called isotopic reactors. Research reactor can be classified by numerical value of the maximum neutron flux density. First class reactors include a high power installation with a high neutron flux density. Such reactors are called high flux. The total number of operating reactors of this class is about 10 in the world. The lower limit of thermal neutron flux in these reactors is the 10 in power of 15 neutrons per cubic centimeters per second. Second class of reactors is average neutron flux density reactors were considered as high flux a few years ago. The neutron flux is upper than 10 in power 14 and upper numerical of neutron flux is 10 in power of 50. The class 3 of these reactors is called it's low neutron flux density, less than 10 in power of 14. There are many such reactors, and they are diverse, they are inexpensive, and used in conduction of different experiments with where some neutrons are needed. Next slide, please. Research reactors also can be classified by their operating mode, determined by the law of reactor power change over the time. The reactors with the steady state neutron flux density are designed for long-term operation at any power level. In this sense, they are no different from the power reactors. Pulse reactors operate in the mode of short, powerful, explosive flashes separated by a long time intervals. And the pulsing reactors are similar to the pulse, but the pulse repetition frequency is about 100 Hz. Pulsing reactors also include subcritical systems that call the boosters to amplify neutrons pulse generated by external source. And the research reactors also can be classified by neutron spectra. In this category includes reactor with the fast or thermal neutron spectra. Neutron energy are important in experiments aimed to study the properties of material in special operating mode, as well as the production of different isotopes. According to the level of technology, research reactors are divided by 4 generations. The first generation of reactors were experimental installation for mixed military and research purposes. One such reactor was Chicago pile. Since uranium enrichment and had not yet been put on industrial basis, only the natural isotopic mixture of uranium-238 and uranium-235 could be used as the fuel. The launch of Chicago pile proved the possibility of chain reaction in natural uranium graphite system. The second generation reactors were built with an understanding of the goals and objectives. These were medium flux reactors by modern standards. intended for research in the field of nuclear physics and related disciplines. At the moment, almost all second-generation reactors have either been decommissioned or upgraded to generation 3 or 3+. Third-generation reactors are reactors that were created not just for research purposes, but also with the conviction of commercial benefit. These reactors are equipped with modern control and protection systems, a set of production equipment, and are rather high-tech multifunctional research and production centers. And the fourth generation reactors is the unique installations currently being built in the single quantities. Example of such installations can be FRM in Germany or Opal in Australia. These reactors combine the principles of natural safety and high performance. So let's move to the specific application of nuclear reactors in various areas of science and technology. And the first will be education. Science, since highly qualified people are at the core of any direction of human development, nuclear reactors and other nuclear installations are primarily used to train specialists. To improve the quality of training process, digital twins of existing nuclear facilities are being developed. Students are being trained at the specific nuclear facilities, and also international cooperation is being expanded to train university students. Present nuclear technologies closely coexist with many other fields, such as medicine, agriculture, biology, chemistry, artificial intelligence, and many others. Thus, the training of multidisciplinary specialists capable of working in the intersection of classical science is now very relevant. The next major direction is nuclear medicine. The application of nuclear technologies in medicine can be divided in two areas. First, it's the application of radiation from nuclear installation, and the second is the application from radiation isotopes. The first area includes radiation therapy with gamma rays, neutrons, protons, and electrons. And the second area includes the use of diagnostic, therapeutic, and theranostics radioisotopes. Next slide, please. The radiation therapy is the one of most popular methods for treating cancer. However, the greatest effectiveness is observed when we combining chemotherapy, surgery, and radiation therapy. When using beams of charged particles, such as electrons and positrons, the therapeutic effect is achieved through the ionization of DNA, as well as through the radiolysis of water as the main component of cell cytoplasm. A reduction of the dose to healthy tissues of the body lying in the path of radiation penetration and surrounding the tumor is achieved through the precise positioning of the patient, the use of complex collimators, and the fractional exposure to the tumor from several sites. Fast neutron therapy utilized high energy neutrons to treat the cancer. Most fast neutrons therapy beams are produced by reactors, cyclotrons, and linear accelerators. The effect of neutron on human tissue differs from the effect of charged particle, since the neutron interact not with electron cloud of atom, but with the nucleus. Low letter radiation damage cells predominantly through the generation of free radicals of oxygen. The neutron is uncharged and damage cells by direct effect on nuclear structures. The malignant tumors tend to have low oxygen levels and thus can be resistant to the low lead radiation. That gives the advantages to neutrons. First advantage is generally shorter treatment cycle. To kill the same number of cancerous cells, neutrons require 1/3 of effective dose as protons. The efficacy of neutron beams for use on prostate cancer has been shown through some clinical trials, and also fast neutron therapy has been applied successfully against gland tumors, adenoid cystic carcinomas, and various number of different cancers on human body. Next. So we can also enhance the therapeutic effects of neutron radiation by using absorbing elements such as boron or gadolinium. Neutron capture therapy is a type of radiotherapy for treating locally invasive tumors such as primary brain tumors, recurrent cancer of head and neck region, and cutaneous and extracutaneous melanoma. This is the two-steps process. First, the patient is injected with tumor localizing drug containing the stable isotope, for example, the boron-10. Which has a high ability to capture low energy, so-called thermal neutrons. In the second step, the patient is radiated with the epithermal neutrons that after losing energy, they stay thermal neutrons and captured by boron-10. In the result, we have nuclear reactions yields high energy alpha particles that kill the cancer cells that taken up the boron atoms. So all clinical experience with neutron capture therapy is with the boron-10. But this method, because of boron, this method calls boron neutron capture therapy. But we have opportunity to use another non-radioactive isotope such as gadolinium, but this research are limited by only experiment with animals, domestic animals and laboratory animals, and has not been done in clinically. BNCT has been evaluated as an alternative method for radiation or for cancer treatment, and now it's only in experimental stage. But at the beginning of the technology, research reactors were used as neutron source, which has advantages and disadvantages. The main disadvantages were operational difficulties to locate in clinic, and issues with the handling of nuclear fuel. As neutron capture therapy technology developed, specialized accelerators appeared that could be placed directly in clinic. And currently, neutron capture therapy technology is still experimental, but the clinical studies are being conducted in Japan, Finland, China, and Sweden. Let's take a closer look to the use of radioisotopes for medical purposes. Over the 50% of all produced radioisotopes used in nuclear medicine. Due to the ability to emit beta particles and gamma rays, radioisotopes is ideal for diagnostic of various diseases. For example, fluorine-18 used for diagnostics using positron emission tomography, visualization of tumor of various localization, assessment of glucose metabolism, and in the myocardium, lungs, brains, and for diagnostics of Alzheimer's disease and many etc. Iodine-123 used for diagnostics using the gamma cameras of the thyroid glands and the nervous system of the heart. Xenon-133 is used for study of lung functional, central, and peripheral hemodynamics, etc. And technetium-99 used for diagnostics of different kinds of diseases. All of diagnostic isotopes, the technetium-99 is the most popular. However, it has a short lifetime, which is approximately 6 hours. So it does not allow to be to transport these isotopes over the long distance from the place that it's was product. The solution of this problem was found in the using of parent radioisotopes molybdenum-99, whose half-life is 66 hours, that which allow us to expanding the delivery zones of these isotopes. Radionuclide generators is a device which provides a local supply for a short-lived radioactive substance from the decay of longer life parent radionuclides. The generator provides a way to separate the desired product from the parent. Generators provide radiation shielding for transport and to minimize the extraction work done at the medical facility. A typical dose rate at the 1 meter from the technetium-99 generator is up to 50 microsieverts per hour during the transportation. These generators output declines with time and must be replaced weekly, since the half-life of molybdenum-99 is still only 66 hours. Since the half-life of parent radionuclide is much longer than of the daughter radionuclide, technetium-99, 50% of equilibrium activity is reached which within one daughter half-life and the 75% with the 2 half-lives of daughter element. So removing the daughter element, it's called the elution process from the generators that called the milking the code, is reasonably done as often as every 6 hours in molybdenum technetium generators. And also generators are used for several isotopes. Radioactive isotopes are capable for accumulating in various areas of human body. However, in order to increase the ability of an isotope to accumulate in certain part of the human body or in inflamed organ or tumor, radioactive radioisotopes are combined with pharmaceuticals. In this way, radiopharmaceuticals are obtained. Depending on the form of the radiopharmaceuticals, it is possible to achieve visualization of process in oncology, of early stages of disease. However, the production of radio pharmaceuticals must be located in so-called clean rooms, organized with according to GMP standards that can provide any single dust in this room. In order to increase the ability of medical institutions or our other organization to use the radiopharmaceuticals, so-called cold kits have been developed. Cold kits is the cold kits for radiopharmaceuticals. By its definition, it's any sterile and apirogenic non-radioactive preparation or set of reagents that once combined with the radionuclide solution without any further chemical purification yields the final radiopharmaceuticals product. Currently, a large number of different cold kits has been developed that allow the synthesis of radiopharmaceuticals in various clinics for a wide range of diagnostic procedures. Next, please. In essence, therapeutic radioisotopes differ from diagnostic ones in their radiation is localized near that its isotopes. This type of therapy is called brachytherapy. So it's the form of radiation therapy where a sealed radiation source is placed inside or near the area required to be irradiated or required to be treatment. Brachytherapy is commonly used and as an effective treatment for several prostate cancer, breast and skin cancer, and also can be used in many other body sites. The treatment results demonstrate that the cancer cure rates of brachytherapy are comparable with the surgery and external beam radiotherapy. And in some cases, it's even better. The features of brachytherapy is the irradiation effects only in the very localized area around the radiation sources. Exposure of radiation to healthy tissues farther away from the sources is reduced. In addition, if the patient have some moves or if we have some movements of the tumor within the body during treatment, the radiation source retained their correct position in related tumor. These characteristics of brachytherapy provide advantages over the external beam radiotherapy, and the tumor can be treated with the very high doses is localized near the tumor and prevent radiation of normal tissues. And the final step of technology of using radioisotopes is theranostics. Theranostics, also known as theragnostics, is a technique commonly used in personalized medicine. For example, in nuclear medicine, one radioactive drug is used to both identify the disease and to treat. In other words, theranostic combine radionuclide imaging and radiation therapy with targets specific biological pathways. Technologies that used for theranostic imaging include radio tracers, contrast agents, positron emission tomography, and magnetic resonance imaging. So it can be used to treat thyroid cancer and neuroblastomas. Personalized medicine also referred to the precision medicine in medical models that separates people into different groups with medical decisions and being tailored to the individual patient based on their predicted response and the risk of disease. Thanks to the use of all possible diagnostics and treatment methods, personalized medicine now allow us to make the diagnosis of disease at early stages and with the using of modern technologies, including AI, we can plan therapy with the maximum efficacy for a specific person. Next slide. So now I think we should make the brief, well, maybe break, shorter, maybe 15 minutes. And after that, I will continue. Okay. Short break. Yeah. Between.
Mikael, let's finish this session until Q&A, and then we have a break. Is it okay for you?
Okay.
Okay. So you break first, and then we give the second talk to Mr. Arton. Wait, Mikael. Oh. All the presentation
So
will be presented by.
maybe some have any question for the first part of my lecture.
Okay. I think Pak Edigiri present your topic, and then he takes a break, small break. Yeah. Now, yeah. Present.
Okay, very good afternoon. My name is Edi Rahman Putra. Now I would like to present regarding about the BRIN's program, relate for the young talents development, of young talents engagement. But please allow me to speak in Bahasa because this is very important for the students now, who are joining this event this morning. So please, my presentation. Ya, baik. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih. Saya ingin menyampaikan paparan terkait dengan program-program apa saja yang ada di BRIN dalam rangka untuk membangun talenta, riset, dan inovasi kita ke depannya. Bisa slide show? Oke, baik. Bisa di slide show? Ya, next. Baik, ada hal penting yang ingin kami sampaikan di sini terkait dengan bagaimana kebijakan pemerintah membangun SDM unggul ke depan. Sebuah regulasi Peraturan Presiden Nomor 108 Tahun 2024 kemarin, pemerintah sudah mencanangkan apa yang disebut dengan namanya manajemen talenta nasional. 3 bidang fokus yang menjadi bagian dari manajemen talenta nasional adalah 1, terkait riset dan inovasi, 2, terkait dengan seni budaya, dan yang ketiga terkait dengan olahraga. Karena apa? Kemajuan suatu bangsa itu bisa dilihat dari bagaimana bangsa tersebut bisa menguasai ipteknya, bisa menguasai terkait dengan bidang olahraganya, menjadi juara dunia, menjadi juara olimpiade dan sebagainya, dan juga bagaimana memberikan pengaruh terhadap seni budayanya terhadap negara lain. Ya, jadi inilah sebenarnya pemerintah sudah menggulirkan sebuah kebijakan yang kita akan coba implementasikan di tahun-tahun mendatang, khususnya di tahun 2025 sampai dengan 2029 ini. Nah, tentunya ada 3 kementerian yang ditugaskan untuk mengkoordinasikan ketiga bidang fokus terkait dengan manajemen talenta. Dan BRIN diamanahkan untuk bisa mengkoordinir terkait dengan program-program manajemen talenta di bidang riset dan inovasi. Lanjut. Program ini tentunya adalah bagaimana kita memiliki sebuah program ya secara terintegrasi, secara holistik, dan secara berkesinambungan dari sejak yang sebelah kiri, the young talent, ya, start from the student, ya, terus kita engage mereka dengan beberapa program, baik itu untuk yang sekolah ke S2, magister, PhD, ya, sampai dengan yang lebih jauh lagi ke postdoktoral dan seterusnya. Inilah skema yang sudah kita terapkan di BRIN. Dan hari ini, HACKATOM itulah bagian dari mana kita bisa mengengage ya, talenta-talenta muda kita di level mahasiswa, terutama mahasiswa tingkat akhir, untuk kita bisa engage menjadi talenta unggul ke depannya, khususnya di bidang kenukliran. Ya, jadi banyak sekali program di sini bagaimana kami bekerja sama dengan perguruan tinggi, jelas. Karena apa? Di perguruan tinggilah tempatnya talent pool, yang talent pool ada di perguruan tinggi. Ya, nah inilah maka salah satu bagian yang kita lakukan pada hari ini adalah bagaimana kita mengengage talenta-talenta muda kita di bidang riset dan inovasi. Lanjut. Lanjut. Lanjut ya. Ya. Baik. Balik lagi sebelumnya. Nah, kita bisa lihat di sini ini adalah skema-skema program-program yang sudah kita lakukan di BRIN selama tahun 2022 kemarin sampai dengan tahun 2024 kemarin. Ya, kita bisa lihat di sini, ya, ada yang namanya Research Student Competition, ARI Fair akan diselenggarakan pada tahun ini bulan September Oktober, juga termasuk HACKATOM. Ya, kita establishkan mulai tahun ini dalam rangka bagaimana kita mengengage talenta muda kita. Ya. Kemudian juga ada bantuan riset buat mahasiswa, ya, for the student. Ada juga kegiatan magang, ya, untuk terutama adalah mahasiswa-mahasiswa di S1. Tapi ke depan kita akan mulai lebih fokus kepada mahasiswa di level S2 dan S3. Karena disitulah fungsinya BRIN bisa mengengage ya talenta muda untuk masuk ke S2, masuk ke S3, ikut postdoc, ikut joint research dan sebagainya dalam rangka untuk bisa meningkatkan kapasitas talenta-talenta muda kita, teman-teman mahasiswa semua. Ya, kita ada program S2, S3 dengan konsep degree by research atau dengan LPDP, kerjasama antara BRIN dengan LPDP, ada sebagai RA, sebagai postdoc, mengundang profesor, dan yang paling tinggi levelnya adalah ketika mereka, talenta-talenta unggul ini sudah berkontribusi kepada negara, pada bangsa, maka kita juga ada program yang memberikan apresiasi kepada mereka. Ada yang namanya Habibie Prize, ada yang namanya Nurtanio Award, ada yang namanya Siwa Besi Award. Adalah bentuk apresiasi dari pemerintah kita kepada talenta unggul kita yang telah memberikan jasa yang luar biasa atas kemajuan iptek ini lakukan selama masa hidupnya. Jadi inilah BRIN yang begitu banyak skema dan program dalam rangka untuk bisa menguatkan, mengembangkan talenta, sejak talenta muda hingga menjadi talenta unggul di bidang riset dan inovasi. Lanjut. Ya. Oke, sekarang apa strategi BRIN terkait dengan iptek nuklir? Kita mulai dengan Yogyakarta. Di Yogyakarta ini, ya, kita akan bangun yang namanya kawasan sains, teknologi, dan edukasi di bidang kenukliran. Ya, kenapa? Karena di sini ada reaktor, ada beberapa fasilitas nuklir, dan tentunya juga Yogyakarta dikenal sebagai kota pelajar, kota pendidikan, dan semua akan menjadi pusat pendidikan terkait dengan nuklir, tidak hanya buat nasional, tapi kita akan coba usahakan menjadi tingkat ke regional, bahkan ke global. Ya. Kemudian yang berikutnya adalah Serpong. Di Serpong kita beri nama adalah Kawasan Sains dan Teknologi B.J. Habibie, di mana ada advance reaktor riset ada di sana, sehingga kita bisa melakukan riset-riset advance yang terkait dengan pemanfaatan nuklir dan radiasi. Terkait dengan bahan bakar, terkait dengan reaktor nuklir, terkait dengan safety, terkait dengan limbah, semua riset akan ada dilakukan di Serpong. Dan terakhir, itu ada di Pasar Jumat, kita sebut dengan kawasan sains dan teknologi Besi, yang lebih dikhususkan adalah bagaimana memanfaatkan nuklir dan radiasi. Khususnya di bidang kesehatan dan industri, makanya di kawasan ini akan dibangun beberapa iradiator, mesin berkas elektron untuk dapat dimanfaatkan secara komersil di bidang kesehatan, di bidang industri, pertanian, dan sebagainya. Jadi kita bisa lihat suatu siklus ya yang secara bertahap. Pertama kita bangun manusianya di Jogja, kemudian kita bisa menguatkan kapasitas riset mereka di Serpong, dan mereka bisa mengimplementasikan hasil-hasil riset pemanfaatan nuklir yang dipusatkan di kawasan Jakarta disebut dengan Besi. Lanjut. Nah, apa yang akan dilakukan di Serpong? Saat ini akan beberapa kegiatan riset yang bisa dimanfaatkan oleh mahasiswa, baik mahasiswa S1, S2 maupun S3. Lanjut. Ya, kami akan jelaskan nanti ya, karena saat ini akan ada beberapa kegiatan yang bisa dilakukan oleh mahasiswa bersama-sama dengan para peserta BRIN. Lanjut. Oke, nah balik lagi. Yang paling penting adalah semua ini bermula tentu dari kebijakan. Ya, kita bisa lihat di sini Undang-Undang 59 tahun 2024 terkait dengan rencana pembangunan jangka menengah sudah di-state bahwa nuklir tidak lagi menjadi the last option untuk new renewable energy, ya, tapi nuklir sudah menjadi salah satu opsi. Artinya apa? Secara mau tidak mau, kita pun juga harus menyiapkan, terutama adalah sumber daya manusianya. Nah, untuk itulah tadi kita kan setelah ada undang-undang diturunkan menjadi sebuah perpres terkait dengan manajemen talenta, bidang riset inovasi, kemudian di BRIN juga mengeluarkan sebuah strategi, ya, kebijakan strategis terkait dengan nuklir dan radiasi, termasuk juga beberapa aktivitas kegiatannya yang terkait dengan penukliran, yaitu membangun akselerator dan juga terkait dengan bagaimana merevitalisasi fasilitas nuklir yang ada di Serpong. Dan yang terakhir yang paling kanan terkait dengan pendidikan, karena di BRIN ada Poltek Nuklir, maka ini pun juga melakukan perbaikan kurikulum. Poltek Nuklir sekarang lebih fokus ya pembelajarannya terkait bagaimana memanfaatkan nuklir untuk energi, bagaimana memanfaatkan nuklir untuk industri, nuklir untuk kesehatan, dan tentunya juga pemanfaatan nuklir untuk karakterisasi material atau bahan. Jadi inilah sebenarnya yang kami lakukan di BRIN, bagaimana kami menyiapkan, ya, mengakselerasi penyiapkan kapasitas talenta muda kita untuk bisa menguasai iptek nuklir ke depannya. Lanjut. Nah, bagaimana dengan hari ini? Hari ini kita kedatangan tamu, ya, there's so many guests, colleague from Russia, especially from Tomsk Polytechnic, ya. Ada beberapa skema yang ditawarkan bagaimana kita bisa studi ke Rusia terkait bidang penukliran. Tentunya Russian government provides several scholarship, ya. Ada Rosatom scholarship, kemudian juga ada IAEA Marie Curie scholarship yang bisa dimanfaatkan secara langsung oleh teman-teman mahasiswa, ya. Dan setelah mendapatkan, mereka bisa studi di Rusia. Ada juga LPDP reguler, ya. Dan tentunya di BRIN memiliki beberapa skema, ya, yang bisa juga dimanfaatkan, ya, oleh teman-teman mahasiswa untuk lanjut ke S2 maupun ke S3. Kami di BRIN punya yang namanya LPDP BRIN Targeted Scholarship, ya, punya beasiswa khusus antara kerjasama BRIN dan LPDP untuk ke S3, ya. Kemudian BRIN juga memiliki program yang namanya Degree by Research, ya. Jadi pendidikan pasca sarjana S2 maupun S3 yang berbasis riset. Jadi praktis tidak di course di kelas, tapi lebih banyak waktunya dihabiskan di lab, ya, di laboratorium, ya, bersama kami dan bersama para periset yang ada di pusat-pusat riset. Dan yang terakhir, BRIN juga memiliki namanya Joint Research Visit. Mahasiswa bisa terlibat di dalam program ini, ikut bersama-sama dengan periset yang ada di BRIN, melakukan kegiatan riset, ya. Contoh yang selalu ini kita lakukan adalah banyak mahasiswa yang terlibat riset yang dilakukan teman-teman di ALIS, di CERN. Kalau kita tahu, CERN itu adalah fasilitas terbesar, ya, terkait dengan collider, dan itu setiap tahun kita mengirimkan periset kita dan juga bisa mengajak mahasiswa yang punya interest terhadap bidang-bidang yang relasi dengan high energy physics, ya, begitu, ya, dan itu sangat terbuka sekali. Nah, yang kanan adalah contoh dari beberapa mahasiswa kita yang sedang sekolah S3, ada juga S2 dengan program Degree by Research, ya, di Tomsk Polytechnic, ya. Dan ini adalah kohort pertama kita, sudah berjalan 2 tahun, dan tentunya di tahun ini akan kita kirimkan yang kohort kedua, dan akan ada kohort-kohort yang berikutnya. Ya, inilah yang sudah kami lakukan, ya, terkait dengan program pendidikan untuk S2, S3, Degree by Research dengan kolaborator kami yang ada di Rusia. Lanjut. Oke, lanjut. Ini adalah beberapa kampus, nanti mungkin akan jelaskan kampus-kampus mana saja di Rusia yang memberikan program kenukliran dengan support pembiayaan dari Rosatom atau dari pemerintahan Federasi Rusia. Ya, dan Tomsk salah satu perguruan tinggi di Rusia yang memberikan pembelajaran terkait dengan program kenukliran selain MEPI, selain Saint Petersburg dan yang lainnya, saya kira. Oke, lanjut. Nah, di samping kita bisa mengirimkan talenta muda kita belajar dan berangkat ke luar negeri, ya, kita pun juga memiliki skema mengundang expert untuk tinggal bersama kita sampai dengan 3-6 bulan, menjadi bagian dari aktivitas riset, menjadi bagian dari pembelajaran di kampus, ya. Untuk itu kita punya skema seperti visiting researchers, ya, ataupun postdoc untuk bisa terlibat, memberikan atmosfer akademik, memberikan atmosfer riset di tempat kita. Dan ini sudah banyak, saat ini sudah lebih dari 500 selama 2-3 tahun ini para expert dari luar negeri datang ke Indonesia. ya, membantu mengakselerasi penguatan kapasitas kita di bidang riset dan inovasi tentunya. Ya, jadi ini bisa dimanfaatkan dan tentunya kami kami memiliki program bahwa ke depan akan ada beberapa expert ya yang akan stay di Poltek Nuklir ya menjadi bagian dari pembelajaran di Poltek Nuklir khususnya. Dan ini tentunya kita bisa sharing bersama-sama dengan teman-teman dari mahasiswa di kampus-kampus lain. Lanjut. Nah, saat ini we just launched a new project in BRIN. Ya. Quite big project. We have two big project. The first regarding about the accelerator technology development. And the second one about revitalization of our nuclear facilities. Ya, ini adalah sebuah konsep, a new concept. Bagaimana ketika kami ingin mengakselerasi dalam jumlah yang banyak, dalam waktu yang singkat, talenta muda ini bisa berperan, berkontribusi, dan mengembangkan diri untuk meningkatkan kapasitasnya, meningkatkan skill-nya yang terkait dengan penukliran. Ya, jadi kita bisa lihat di sini, semua program kita integrasikan menjadi satu. Ya, ada nanti sebagai riset asisten, ada sebagai mahasiswa degree by riset. Kita bisa mengundang expert datang ke tempat kita, ya, atau kita juga mengirimkan mahasiswa untuk belajar keluar, mengirimkan mahasiswa untuk joint research visit ya ke tempat luar, ataupun melakukan training ya, dan tentunya juga ada yang beasiswa khususnya ya. Jadi saya kira ini adalah contoh bagaimana di BRIN memiliki strategi untuk bisa mengakselerasi ya jumlah dan juga khususnya jumlah dan kualitas dari riset dengan mengimplementasikan yang namanya platform kolaborasi. Lanjut. Ini adalah salah satu contoh terkait dengan akselerator, cyclotron. Ini sudah established, sudah berjalan. Ya, kita bisa lihat kampus-kampus yang menjadi kolaborasinya, menjadi kolaborator dari proyek ini. Ada dari Korea, ada dari Thailand, ya, dan juga ada dari Jepang. Dan ya, saya kira ya itu ya. Dalam rangka untuk bisa mendevelop our first own cyclotron ya 30 megaton volt di Serpong, dan program ini sudah berjalan dan tentunya kita bisa lihat akan banyak melibatkan mahasiswa, lebih dari 50 mahasiswa, dan ini sangat terbuka. Sekarang sedang open call, jadi sering-seringlah lihat website BRIN, sering-seringlah berkomunikasi dengan teman-teman yang ada di bidang penukliran untuk mencari tahu apakah punya peluang untuk bisa involve di kegiatan pengembangan akselerator yang dilakukan di Serpong nanti. Ya, jadi ini sangat terbuka dan kita pun juga kerjasama dengan Gajah Mada, UGM dan UI, ya, untuk bisa memprovide program S2 dan S3 by riset untuk proyek terkait dengan pengembangan akselerator atau cyclotron ini. Ya, kita bisa lihat pendanaannya cukup besar. Dan ini bisa berlangsung beberapa tahun, ya. Dan balik lagi, ini adalah peluang terbaik, peluang emas yang bisa dimanfaatkan oleh teman-teman mahasiswa sebagai talenta muda, as a young talents, ya, to involve with our research project in the BRIN. Ya, lanjut. Oke, terakhirnya adalah beasiswa BRIN LPDP. BRIN saat ini sangat fokus untuk menguatkan talentanya di 4 bidang ini. Bidang yang terkait dengan biodiversity. Kenapa? Indonesia adalah salah satu negara dengan biodiversity yang sangat besar. Jadi mau tidak mau, kita harus fokus menguatkan talenta, menyiapkan talenta unggul kita untuk bisa menguasai bidang yang terkait dengan biodiversity. Yang kedua, bidang kelautan dan laut dalam. Jangan lupa, Indonesia itu 2/3-nya lautan. dan lebih dari 60% adalah laut dalam, dan itu belum dieksplor, belum digali, belum dimanfaatkan. Ya, jadi BRIN ke depan akan memiliki beberapa kapal riset baru untuk mengeksplor laut dalam kita, menemukan spesies-spesies baru, dan juga kemudian memanfaatkannya tentunya untuk bidang kesehatan, untuk pangan, atau energi, ataupun yang lainnya. Ketiga, bidang terkait dengan space and aeronautics dalam pengembangan satelit tentunya. Karena apa? Kita adalah negara kepulauan, 17.000 pulau, satu-satunya yang bisa melakukan koneksi adalah dengan menggunakan teknologi satelit. Ya, jadi itulah. Dan yang terakhir adalah nuklir dan radiation technology. Jadi kalian beruntung yang memiliki minat di bidang nuklir dan radiasi, kalian punya wadahnya, punya medianya, punya jalannya untuk bisa mengembangkan kompetensi kalian, kapasitas kalian, dan juga karir kalian ke depannya. Lanjut. Ya. Kesimpulan, banyak scholarship yang bisa kalian manfaatkan. Rosatom, ya, Russian Government, Russian Federation, punya beberapa skema untuk bisa dimanfaatkan untuk kalian sekolah S2, S3, ya kan? Kemudian juga ada tadi IAEA Marie Curie Scholarship, ya, untuk semua subjek dan beberapa universitas di Indonesia, termasuk di Rusia. Ada LPDP reguler, kalau kalian lihat di situ, ada beberapa perguruan tinggi di Rusia yang bisa memprovide terkait dengan program BRIN atau ikut program LPDP BRIN targeted. Ya, yang memang spesifik, salah satu bidangnya adalah bidang yang terkait dengan penukliran. Ya, meskipun pada saat ini kita belum punya kerjasama dengan Rusia untuk yang LPDP targeted ini, karena masih fokus di akselerator teknologi. Ya, kita bisa lihat, tapi itu juga bidang nuklir. Ya, dan saya kira juga kesempatan bisa dimanfaatkan oleh mahasiswa-mahasiswa karena nuklir tidak senantiasa terkait dengan reaktor. Future technology about nuclear is accelerator technology. Ya, jadi ini juga kesempatan buat teman-teman mahasiswa untuk bisa terlibat di kegiatan ini. Dan yang terakhir, degree by riset, ini adalah program dari BRIN khusus, ya. Ini kita sudah punya kerjasama dengan Toms Politeknik dan mudah-mudahan juga akan kita expand ke kampus lain dan tentunya dengan kampus dalam negeri ada di ITB dan UGM. Oke, saya kira mungkin itu. Lanjut. Ya, ini mungkin message yang paling penting dan mungkin tidak semua tahu atau mendalaminya, bahwa sebenarnya ini adalah sebuah statement di era Soekarno. Ya, bahwa pada saat meresmikan reaktor pertama di Bandung, Trigama di Bandung, Soekarno sudah men-state bahwa untuk bisa menguasai ITEK itu ya tinggal dua, kenukliran dan antariksa. Ya, makanya di BRIN juga nuklir dan antariksa menjadi fokus yang khusus. Ya, kita punya programnya, kita punya semua skemanya. Karena apa? Karena disinilah sebenarnya kapasitas kita, kemampuan kita untuk bisa menguasai ilmu dan teknologi yang memang advance sekali. Jadi terkait dengan nuklir bukanlah isu yang sekarang, tapi isu-isu yang sudah dimulai sejak saya belum lahir, ya tentunya. Pak Jula juga belum lahir ya. Tahun 60-an sudah dimulai isu ini dan banyak sekali sebenarnya kegiatan dan kolaborasi yang dilakukan oleh Indonesia dengan pihak luar, ya, terkait dengan pengembangan ITEK nuklir, termasuk juga dengan Rusia. Saya kira itu saja pesan dari kami. Terima kasih. Selamat mengikuti kompetensi HACKATOM. Yang pertama, nanti pemenangnya akan dikirimkan ke Rusia dalam rangka 80 tahun nuklir industri Indonesia, dan tentunya kita bisa engage dengan program-program lainnya buat mahasiswa yang tertarik. Ya, silakan nanti menghubungi dari tim manajemen talenta yang ada di BRIN atau ikut dalam akun IG saya kalau mau, ya. Nanti kalau bisa login aja ke akun IG saya, banyak informasi yang saya sharing, tidak hanya kenukliran tapi juga bidang-bidang lain. Selamat berlomba, terima kasih untuk perhatiannya, dan nuklir untuk masa depan. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Oke,
Thank you, Pak Edi, for your presentation. And adik-adik mahasiswa, if you have question, keep it for now. We'll have a Q&A session later after this panelists finish their presentation. Now, Mikhail can continue your presentation.
So, yeah, from here. Yeah. So now let's continue with my presentation about nuclear technologies. And now we move from medical application to nuclear technologies in their application in technology. Next slide, please. Next, please. Okay. It's the neutron transportation doping. In order to use the silicon in the semiconductor industry, it must be doped. Doping is the intentional introduction of impurities into a semiconductor for the purpose of modulating its electrical, optical, or structure properties. The doped material is referred to as an extrinsic semiconductor. Doping can be carried out by various ways: ion implantation, chemical doping, and others. However, in order to obtain a highly homogeneous distribution of impurities, the neutron transmutation doping is the only possible method. The reaction of radiation capture of the silicon 30 isotope is the interest for this purpose. Due to this reaction, the radioactive beta-active isotope silicon 31 is occur, and with the half-life of 157 minutes, it's decayed to the daughter isotopes phosphorus 31, which is dopant that allow obtain n type of conductivity. Next slide. As the rule, nuclear reactors are used to implement the condition for neutron transmutation doping. Many research reactors, as well as channel type power reactors, can dope 4 or 5-inch silicon in diameter. However, the most promising is the doping of 8-inch silicon, and installation for this doping is the unique equipment that only available in at the 5 research reactors. It's the APAL in Australia, IRTT in Tomsk Polytechnic University, FRM2 in Germany, BR2 in Belgium, and the Hanara in Korea. Next, please. After irradiation of silicon, it is necessary to wash off surface from the radioactive contamination, and after that we need to perform the high temperature annealing to get rid of negative changes in the crystal lattice of silicon. It is also necessary to have quality control equipment, including measuring the specific resistance of ingots and the lifetime of main charge carriers. Next technology is gemstone irradiation. Nuclear technology are also used in jewelry industry. Gemstone irradiation is the process in which gemstones are internationally exposed to high flux of ionizing radiation in order to enhance its optical properties. Ionizing radiation can rearrange the gemstone's crystal structure, altering to its optical properties. This can significantly alter the gemstone's color or lessen the visibility of its inclusions. The process widely practiced in jewelry industry is done in either a practice accelerator or for electron irradiation and in gamma ray facilities using the radioactive isotopes of cobalt-60. Or in the nuclear reactors for neutron irradiation, and its irradiation treatment has enabled the creation a gemstone's color what does not exist in the nature at all. However, the process it's done in a nuclear reactor. It can make gemstones radioactivity. Certain natural gemstones colors such as blue to green colors of diamonds or red colors of zircon are caused by exposure of natural irradiation in the Earth, which is usually alpha particle or beta particles. But the limited penetration ability of this type of radiation results in the particle coloring of the gemstone's surface, not only all volume of its stone. The most commonly irradiated gemstones is the topaz, which usually becomes blue after the irradiation process. Intensely blue topaz does not exist in the nature, and its blue color is caused by artificial irradiation. According to the American Gem Trade Association, approximately 6,000 kilograms of topaz are irradiated every year globally. Dark blue varieties of topaz includes American super blue and London blue are caused by neutron irradiation, while lighter sky blue ones are often caused by electron irradiation. And for example, Swiss blue color is caused by contamination of two of these methods. Radiation coloring can be applied to many other precious and semi-precious stones. Another application of nuclear technology is the so-called nuclear battery. Nuclear battery use energy from radioactive decay of the radioactive isotope to generate electricity. Like a nuclear reactor, it generates electricity from nuclear energy, but it differs by not using the chain reaction, but using the decay of radioisotope. Although commonly called batteries, atomic batteries are technically not electrochemical and cannot be charged or recharged. Although they are very costly, they have extremely long lives and high energy density. So they are typically used in power sources for equipment that must operate unattended for the long periods of time, such as spacecrafts, pacemakers, underwater systems, and automated scientific station in remote parts of the world. A radioisotope thermoelectric generator, so-called RTG, or radioisotope power system, so-called RPS, is a type of nuclear battery that use the array of thermocouples to convert the heat released in by the decay of suitable radioactive isotope into the electricity by the big effect. This type of generator has no moving parts, and it's ideal for development in remote and harsh environments for extended periods with the risk with no risk of parts wearing out of multifunctioning. RTGs are usually the most desirable power source for unterminated situation that needs a few hundred watts or maybe less of power for duration too long to the another fuel cells, batteries, or maybe some generators to provide economically and in places where solar cells are not used at all. It cannot be used at all. RTGs have been used as the power sources in satellite space probes and uncrewed remote facilities, such as a series of lighthouses built in the Soviet Union inside the Arctic Circle. Next, please. Radioisotopes also can be used in the industry. For example, americium-241 used in the smoke detectors, field height detectors, and measuring ash content of coal. Cesium-137 used for radio tracer technique for identification of sources of soil erosion and deposition, as well as density and field height level switches. Chromium-51 used to label sand to study coastal erosion, also as a tracer in study of blood. Cobalt-16, lanthanum-140, scandium-46, together used in the blast furnaces to determine resistant time and the quantity yields of measuring the furnace performance. And many other applications of radioisotopes in the industry. Next, please. And now we move to the next part. I called it nuclear science. Here I will talk about some fundamental problems where the nuclear technology, nuclear science can help us deal with this. Next, please. First of all, it's neutron activation analysis, so-called NAA. It's the nuclear process used to determine the concentration of elements in various materials. NAA allows discrete sampling of elements as it disregards the chemical form of a sample and focuses solely on atomic nuclei. The method is based on neutron activation of those requires a neutron source. Usually, as a neutron source, we use the nuclear reactors, research nuclear reactors of different power level. The sample is irradiated with neutrons, causing its constituent elements to form radioactive isotope. The radioactive emission of these radioactive isotopes, decay paths of each element have long been studied and determined. Using this information, it is possible to study spectra of emission, of radioactive emission, and determine the concentration of various elements with it. A particular advantage of this technique is that it does not destroy the sample. And this has been used for analysis of works of arts and the historical artifacts. NAA can also be used to determine the activity of a radioactive sample. Neutron activation analysis has a wide variety of application, including within the fields of archaeology, soil science, geology, and the semiconductor industry. Neutron activation analysis can detect up to 74 elements depending upon the experimental procedure, with minimum detectors limits regarding from 0.1 to 1 million nanograms per gram, depending on the element under investigation. Heavier elements have large nuclei. Therefore, they have a larger neutron capture cross-section and are most likely to be activated. Some nuclei can capture a number of neutrons and remain relatively stable, not undergoing the transmission or decay for many months or even years. Other nuclei decay is only stable and can only be identified by prompt gamma neutron activation analysis. Prompt gamma neutron activation analysis is a very widely applicable technique for determining the presence and amount of many elements simultaneously in the samples, ranging in size from micrograms to many grams. It's also non-destructive method, and the chemical form and shape of the sample are relatively unimportant. Typical measurements take from a few minutes to several hours per sample. The technique can be described as follows. The sample is continuously irradiated with the beam of neutrons. The consistent elements of the sample absorbs some of these neutrons and emit prompt gamma rays, which are measured with gamma ray spectrometer. The energies of these gamma rays identify the neutron capture element, while the intensities of the peaks at these energies reveal their concentration. The amount of analyzed elements is given by the ratio of count rate of the characterized peak in the sample, and the rate is known mass of appropriate element standards irradiated under the same conditions. Next slide, please. The next technology is the neutron diffraction. And also it called elastic neutron scattering, is the application of neutron scattering to determination of atomic or magnetic structure of materials. A sample to be examined is placed in the beam of thermal on or cold neutrons to obtain a diffraction pattern that provides information about structure of the material. The technique is similar to the X-ray diffraction, but due to their different scattering properties. Neutrons and gamma rays provide complementary information. X-rays are suited for superficial analysis. Strong X-rays from synchrotron radiation are suited for shallow depths or thin pieces of irradiated objects, while the neutrons having higher penetration depths and suited for bulk samples. The neutron scattering is used to detect the distance between atoms and study the dynamics of material. It involves two major principles, elastic scattering and inelastic scattering. Elastic scattering provides insight into the structural properties of materials by looking at the angles at which neutrons are scattered. The resulting pattern of the scattering provides information regarding the atomic structure of crystals, a liquid, and amorphous material. Inelastic scattering focus on material dynamics through the study of neutron energy and momentum changes during the irradiation. It is the key to study phonons, magnons, and other solid materials. Next slide, please. Neutron reflectometry is the also neutron diffraction technique for measuring the structure of thin films, similar to the often complementary technique of X-rays, reflectivity, and the ellipsometry. The technique provides valuable information over the wide variety of scientific and technological application, including chemical aggregation, polymer and surfactant absorption, structure of thin films, magnetic systems, biological membranes, and many, etc. It has become a technique widespread at the reactor and spallation sources of neutrons, which a wide range of available fitting software and standardized data formats. The technique involves using the highly collimated beams of neutrons onto an extremely flat surface and measuring the intensity of reflected radiation as the function of the angle of neutron wavelength. The exact shape of the reflectivity profile provides detailed information about the structure of this surface, including the thickness, density, and roughness of any thin films layered on the substrate. Neutron reflectometry is the most often made in specular reflection mode. There, the angle of the incident beams is equal to the angle of reflected beams. Neutron tomography is the form of computated tomography involving the production of three-dimensional images by the detection of the absorbances of neutron produced by a neutron source. It creates a three-dimensional image of an object, combining multiply planar images with the known separation. It has a resolution of 25 micrometers. While its resolution is lower than in X-ray tomography, it can be useful for materials containing low contrast between the matrix and the object of interest. For instance, fossils with the high carbon content, such as plants or vertebrate remains. Neutron tomography can have the unfortunate side effect of leaving images samples radioactive if they contain appreciable levels of certain elements such as cobalt. And however, in practice, the neutron activation is low and short life. Such methods is considered in like a non-destructive. The next step of the neutron scattering is the small angle scattering, so-called SENS. SENS is an experimental technique that uses elastic neutron scattering at small scattering angles to investigate the structure of various substances as at mesoscopic scale about 1 to 100 nanometers. Small angle scattering is in many respects very similar to small angle X-ray scattering. Both techniques are jointly referred to as small angle scattering, and the most important feature of this technique, this is its potential for analyzing the inner structure of disordered systems. And the frequency of application of this method is the unique way to obtain direct structural information on systems with the random arrangement of density in homogeneous in such large scales. The crucial feature of SANS that makes it particularly useful for the biological science is the special behavior of hydrogen, especially compared to deuterium. In biological systems, hydrogen can be exchanged with the deuterium, which usually has minimal effect on the sample, but has dramatic effects on the scattering. And the next scattering technology is the grazing incidence small angle scattering, so-called GSAS. Is the scattering technique used to study nanostructural surfaces and thin films. The scattered probe is either photons or neutrons. GSAS combines the accessibility length scales of small angle scattering and the surface sensitivity of grazing incidence diffraction. A typical application of this technology is the characterization of self-assembly and self-organization of nanoscale of thin films. Systems studying by GSAS include quantum dot arrays, growth instabilities formed during in situ growth, self-organized nanostructures in the thin films of block polymers, silica mesophases, and nanoparticles. Next, please. And finally, a few words about ultra-cold neutrons. In common, standard neutrons have kinetic energy around 0.0025 electro-eV at the 20 degrees of Celsius. But if we use the cryogenic temperature, we can obtain so-called ultra-cold neutrons. Such neutrons can help us with some fundamental problems such as measurement of neutron lifetime, measurement of neutron elastic dipole moment, observation of the gravitational interaction of neutrons despite of the neutron is neutral particle, search of neutron in micro neutron oscillation, and the measurements of A coefficients of the neutron beta decay correlation. Next slide. So that's all in nuclear technology in non-energy purposes. So, next.
Thank you, Mikhail. Do you mind if you take question after two other panelists in Zoom speech? Is it okay? Okay. Okay. Good. Zoom. So now we already have with us two other panelists from Zoom. They are Ms. Vera and Naba.
So, good morning, dear colleagues. Good morning, dear students. Can you hear me?
Hi, Vera.
Morning. So, this is very nice to see you. And I would like to welcome all of you on behalf of Rosatom State Corporation. And I represent the project office for education development and international cooperation. And I would like you to tell you more about how to learn all those amazing things described by the previous speaker. But I think I will need your assistance with the presentation, please. Can you see the presentation?
Is it from you, from your side? Okay.
No.
Ready.
Yes. No. Next slide. Next slide, please. Dear colleagues, can you show the next slide, please? I think there is a small technical issue. I'm sorry. So, but before the presentation starts, I would like you to tell some words about what we are doing. So, as you know, Rosatom is one of the global leaders at the market of the nuclear technology in the world. So we have over 80 years of experience in my presentation. So thank you very much, colleagues. So can you show the next slide, please? Yes. So we have over 80 years of experience in operating, constructing, and maintaining various nuclear facilities, starting from uranium ore mining, constructing nuclear power plants, research reactors, producing isotopes, and even the only nuclear fleet in the world is also operated by Rosatom. The next slide, please. So, as you probably know, we are the pioneers in the area of nuclear energy in the world. And in 1954, the first nuclear power plant was constructed in Russia in the city of Obninsk. And now we are very proud that we are doing our projects not only in Russia, but in other countries too. The next slide, please. So at the moment, we're also constructing nuclear power plants in our partner countries like Hungary, China, Turkey, Egypt, India, Bangladesh, and also we are constructing the centers of nuclear science and technology. And of course, we understand that the success of any nuclear project depends on the highly qualified people. That is why we pay a lot of attention to the human resources development and education. The next slide, please. So Rosatom holds a very wide range of various activities aimed at the personnel training, education development, starting from strategic planning of human resources development for our partner countries, to teaching international students at the Russian universities, developing cross-university cooperation, and providing various activities for those who would like to get further education, like professional development and upskilling programs. The next slide, please. For the recent 12 years, Rosatom have developed the whole educational ecosystem, starting from the secondary schools, colleges, universities, both in Russia and abroad. And also we have two academies, Rosatom Technical Academy, that is responsible for hard skills, theoretical training and practical training. And actually this is the center of excellence for training personnel for nuclear power plants. And also we have Rosatom Corporate Academy that provides a wide range of programs and leadership and soft skills. The next slide, please. We work hand in hand with Russian leading universities, and at the moment we do cooperate with over 20 Russian schools. Among them there are National Research Nuclear University MEFI, Tomsk Polytechnic University, Mrs. National University of Science and Technology, St. Petersburg Polytechnic University, and many, many other universities in Russia that provide various programs at nuclear and related areas. The next slide, please. We do cooperate in 4 main directions, and the one of them is teaching international students at the Russian universities in nuclear and related fields. At the moment, there are over 2,200 international students from 65 countries of the world doing their degrees in Russia. So I must say that all of those students study free of charge because we provide the scholarship of the Russian government to cover their tuition fees. Also, Rosatom supports the development of the national systems of nuclear education through cross-university cooperation, providing lectures, seminars, developing joint academic programs, and opening branches of the Russian universities. And also, we provide professional development programs for the professionals and university faculty members and support international networking. The next slide, please. All the international students who are studying in Russia in nuclear and related areas have to do their mandatory practical internship at Rosatom training centers, because we understand that every professional needs to know the equipment he is going to face when he's back home. Either this is nuclear power plant or Center of Nuclear Science and Technology. So we pay much attention to the practical training of all the students. The next slide, please. And also, we support not only students, but the faculty members of the university, the professors, providing them the professional development programs in the format of train the trainers. Those are the short-term programs developing not only the competencies in nuclear technology, but also providing the methodological support for them to be able to develop new academic programs at their home universities in their home countries. The next slide, please. And now I would like to tell you a little bit in more detail about how you can apply to the Russian university if you really want to get a degree in nuclear. Every year, we provide over 300 scholarships for international students. You can apply if you're the citizen of the countries listed here. All of those countries are Rosatom partners. The next slide, please. So the scholarship covers the tuition fees for any level of education, undergraduate degree, master's or PhD, and also it covers the specialist degree, which is normally 5.5 years. So the tuition is full-time, all only in person, and the academic programs can be provided either in Russian or in English. The scholarships that we provide cover the tuition fees for the whole period of your education in Russia, including 1 year of Russian language preparatory course if you apply for the program taught in Russian. And also the students get a monthly allowance that usually is enough to cover the living in the students' dorm. And of course, all the students are provided with a practical training at Rosatom training centers. The next slide, please. So the scholarship covers the education in all the levels of education, bachelor, master's, and PhDs. And we provide a wide range of academic programs covering nuclear power engineering, nuclear physics, chemistry, chemical technology, power engineering, material science, and other areas related to nuclear industries. At this slide, you can see some examples of the academic programs you can apply for. The next slide, please. So as I've said, we also can provide you with the master degree or PhD degree. I must draw your attention that PhD degree in Russia usually takes about 4 or 5 years because the postgraduate course is provided in the Russian language only. So 1 year of the Russian language and 4 years of PhD course. The next slide, please. So the students can apply at any of our partner universities. I've told you already that we have over 20 Russian universities who are Rosatom partners, and among them the Tomsk Polytechnic University, MEFI University in Moscow, Mendeleev's Chemical Technology University, St. Petersburg State University, St. Petersburg Polytechnic, and many other schools. The next slide, please. So to apply for an academic program in Russia, students usually need to take 5 main steps. So the application procedure normally starts pretty early. If you want to apply for the next academic year, the student should apply in October of this year. And the application procedure normally starts in mid-October and continues to the mid of January. We understand that it's pretty much difficult to make a final decision about where you want to continue your education this time, but if you want to study in Russia, it's better to apply in advance and complete the application form at the website educationinrussian.com. After application in January, there is the first of selection, stage of selection, when sometimes the Russian cultural centers of the Russian embassy organize the entry tests, or just analyze all the documents or the portfolio of the applicants uploaded to the website. At the beginning of the next year, there is the second stage of the selection, when all applicants have to submit the translation of their documents, like the previous education certificates, medical certificates, and so on. After the second stage of the selection, approximately in June, July, all the students have the notice about if they are selected, and afterwards they are allocated with the host universities. And in summer, they usually get the visa support from the Russian side and can come to Russia at the beginning of September, or the academic year normally starts in September or October. The next slide, please. So, dear students, dear colleagues, this is briefly about what Rosatom is doing in terms of our education and human resources development. And we are open to reply any questions. And here are our contact details. You can contact us anytime, and we will provide you with more detailed information if you want to get nuclear education in Russia and learn more about nuclear technology. Thank you very much for your attention, and I wish you, all of you, good luck during the hackathon, because you know the winners will be able to visit Moscow this September and celebrate the 80th anniversary of Russian nuclear industry. Thank you very much.
Thank you, Vera, for your presentation. Please don't go anywhere because we will have a question and answer later after Naba talk. Thank you. And next, the next presenter is Naba.
Hello, hello everyone.
Hi, Naba.
Hello. Hello, can you hear me?
How are you?
We're fine. I'm fine. How are you?
Yeah.
How are you guys?
We are very happy to have you.
From the Jogja, right?
Okay. Your topic is on sharing session about experience of education in Russia. Is it correct?
Yes, that will be me.
Okay.
Wait, I think.
Time is yours.
Okay. Wait a second. Let me just adjust all of these things. I'm going to share my presentation. Can you see? Can you all see it? Hello? Can you all see all my presentation or?
Yes, that's fine. We can see the presentation.
Okay, thank you so much, Vera. Okay, halo semuanya. Thank you so much to the organizer of the Global HACKATOM Indonesia and BRIN for inviting me to speak at this inspiring event. Once again, my name is Naba and I'm a graduate in Design, Operation and Engineering for Nuclear Power Plant from Ural Federal University in Yekaterinburg, Russia. And I'm also a scholarship awardee from Russian government or Rasatrudnichestva. And I'm also proud to be part of the Russian Nuclear Education Ambassador, or we usually call it RNEA. It's a global initiative that aims to promote nuclear education in Russia and foster any international collaboration in the field. First of all, I'd like to say that I'm very honored to be here, even though I can't join you physically and can only be here online. So please accept my apology for not being there in person. And second of all, I know that we have foreign lecturers for the from the TPU, the Tomsk Polytechnic University. The joining the session today, but I like to apologize because I will deliver my session in Bahasa Indonesia as requested by the event organizers because the target audience is the student from Indonesia. But don't worry, if anyone needs any clarification in English afterwards, I'll be happy to assist. So please bear with me for the rest of the presentation will be in Bahasa Indonesia. Okay. Cukup bahasa Inggrisnya, lanjut ke tujuan saya ya hari ini. Saya di sini mau membawa dua misi sebenarnya. Yang pertama untuk membagikan pengalaman saya kuliah di Rusia selama 6,5 tahun. Karena saya mengambil jurusan, bukan jurusannya, degree-nya itu specialist degree. Dan 1 tahunnya itu adalah untuk belajar bahasa Rusia. Untuk biar nggak kaget saat di dunia perkuliahannya. Yang kedua, saya mau memperkenalkan Erania kepada teman-teman dan murid-murid di Indonesia yang mungkin tertarik bergabung dalam komunitas internasional ini. Nah, sebelumnya mungkin semuanya bertanya ya, kenapa sih harus kuliah di Rusia gitu kan? Jawabannya itu sederhana sebenarnya. Karena Rusia itu adalah salah satu negara yang terdepan dalam teknologi nuklir dan inovasi. Oke, sorry. Dari membangun PLTN pertama di dunia, tadi sepertinya sudah dijelaskan ya sama Ibu Vera, hingga memiliki institusi seperti Rosatom, MIFI, Tomsk Polytechnic University, TPU, atau Ural Federal University, universitas saya. Jadi Rusia itu punya segala fasilitas, riset, dan dosen terbaik di bidang nuklir. Kalau kalian benar-benar serius pengen belajar teknik nuklir sih, Rusia menurut saya sih pilihan yang tepat ya. Nah, selama 6,5 tahun saya tinggal di Rusia dan belajar bahasa Rusia, saya punya banyak kenangan yang tidak terlupakan. Yang pertama itu saya belajar bersama teman-teman dari berbagai negara dan bukan cuma soal teori dan praktikum, tapi kami juga menikmati kehidupan sebagai mahasiswa, foreign mahasiswa lebih tepatnya. Mulai dari belajar bareng di laboratorium. Ini teman-teman saya dan itu ada dosen saya di sini. Menghadapi musim dingin. Kebetulan kota saya itu terletak di tengah-tengah Rusia, tengah-tengah agak atas dikit sih. Jadi kalau misalnya musim dingin itu it's quite cold there. We've been experiencing for minus 42, minus 40. So it's quite cold. Sampai ya untuk keluar aja udah males saking dinginnya gitu. Jadi itu pengalaman belajarnya tuh benar-benar berkesan dan menyenangkan sekali sih bisa berkumpul bersama teman-teman di sana. Bahkan saya juga sempat mengunjungi, ini teman-teman saya segrup, kita semua kebanyakan orang Rusia, bisa dilihat kita dari 30 orang, 4 perempuan dan sisanya laki-laki. dan hanya ada 2 orang foreigner, yaitu saya dari Indonesia dan satu lagi dari Egypt. Nah, bahkan saya dan teman-teman grup saya di universitas juga sempat mengunjungi Belayarskaya AS atau Belayarskaya Nuclear Power Plant di Zaryechny di Rusia pada tahun 2022 kalau nggak salah, atau 2021 ya. I think 2022 deh. Nah, jadi kuliah di Rusia itu bukan hanya akademik gitu, tapi juga tentang membangun pertemanan global dan pengalaman hidup yang that you cannot forget deh. Nah, oke. Lanjut ke Russian Nuclear Education Ambassador. Sebelum saya bergabung dengan Arenia, saya tidak terlalu aktif di luar kegiatan akademik sebenarnya. Tapi setelah masuk Arenia, saya tuh dunianya lebih, khususnya di bidang nuklir ya, lebih terbuka jalannya gitu. Saya mendapat kesempatan banyak untuk berpartisipasi dalam beberapa event. Contohnya, ini adalah Tom Skills tahun 2021, kayaknya 2021 deh, 2021 atau 2022. Nah, ini juga tim kami dari RNEA dan Junior of the Rosatom, kita semua berkolaborasi untuk membuat sebuah booth kecil yang bertemakan Global Village. Jadi booth itu untuk semua partisipan dari Atom Skills itu bisa bermain dan mengenal lebih jauh sih tentang dunia internasional di bidang nuklir lebih tepatnya. Kemudian ada Forsage, ini tahun 2023, terus ini Saint Petersburg International Nuclear Forum kalau nggak salah 2022 sepertinya. Nah, dan juga ada annual event from MIFI dan Rosatom, yaitu Nuclear Education Week di Obninsk. Saya mengikuti Nuclear Education Week itu 2 tahun yang lalu, tahun 2023. Tapi Nuclear Education Week itu baru saja selesai 1 minggu yang lalu di Obninsk. Nah, gitu sih. Jadi saya juga bisa membangun koneksi dengan teman-teman dari berbagai belahan dunia. Karena teman-teman dari RNEA memiliki 54 anggota dari 22 negara. Dan komunitas ini benar-benar saling mendukung sih untuk berkolaborasi antar negara, berbagi informasi, dan kita semua grow up together lah, bisa dibilang seperti itu. Jadi kalau misalnya tertarik dengan Arenia setelah presentasi ini, bisa sih langsung menghubungi saya atau nanti ada dari TPU-nya juga. Satu hal yang saya pelajari dari perjalanan berkuliah di Rusia itu sebenarnya jangan takut ambil peluang, karena sebenarnya kuliah di Rusia itu sepertinya banyak yang nggak pernah kepikiran gitu. Tapi saya melihat pas itu ada pameran di SMA saya kebetulan, terus ada yang invite untuk melihat ini ada Rusia gitu. Jadi setelah saya searching, melihat ada beasiswa, peluang beasiswa, saya apply itu dan dapat. Jadi dan dari satu peluang itu aja saya sudah bisa dapat banyak, sangat banyak ini sih sebenarnya pengalaman juga. Nah, jadi sebenarnya itu aja kali ya. Kali ini saya Naba, terima kasih banyak atas perhatiannya. Saya berharap teman-teman yang hadir di hari ini dan yang mengikuti HACKATOM bisa ikut merasakan pengalaman luar biasa seperti yang saya alami, dan mungkin suatu saat nanti juga bergabung dalam Arenia, dalam satu organisasi ini, karena kuliah di Rusia itu bukan tentang karir dibilang bidang nuklir gitu, tapi juga selalu membangun jaringan global, bersenang-senang dan menciptakan kenangan gitu yang tak terlupakan. Oke, itu aja dari saya. Spasiba is the thank you. Yeah, thank you. Dan
Oh,
kalau misalnya ada pertanyaan bisa langsung ditanyakan aja.
okay, thank you very much, Naba.
Thank you.
Okay, now it's time for question and answer. Pak Edigiri, could you please come to the stage? You have to. Okay. Now we still have about 20 minutes for question and answer. I will ask you two questions. Two questions. Who will ask the question? Two questions first. Okay. Could you please provide mic? Oh, come to the stage. Okay. Please say your name, your university, the
Okay, first of all, thank you very much because of the given opportunities for me. Hello, let me introduce myself first. My name is Jeff Shahom Tarigan. I come from ITS, Institute Technology School November at Surabaya. Actually, I have a question for Dr. Adikin. Actually, I have two questions. Can I those two questions? First is, I have a question about the future research or development of AI in nuclear medicine, such as diagnostic, therapeutic, and theranostic. From your POV, in which area can AI contribute more, and can you give me more example or elaborate explanation in which fields can AI contribute more? And then for the second question, it's about 1, 2, 3I diagnostic isotope. Yeah. The first question is, does the procedure of diagnostic using 1, 2, 3I isotopes can evaluate metabolism of the tissue, just like the PET diagnostic, or is it just like another medical imaging modalities that only show anatomical structure? And second, you mentioned in your presentation that the 1, 2, 3I isotope is considered specifically suitable for thyroid gland and the cardiac nervous system, right? Yeah. Could you explain to me the key concept underlying mechanism that enables 1, 2, 3I isotopes to do its function? Thank you.
Thank you for your question. It's a great one. So first of all, don't answer. First of all, the question for you, what is your specialization?
Okay, I study medical technology in ITS.
Okay, so the first part of your question, you can participate in the field of development of the pharmaceuticals for nuclear medicine. You can study the mechanism of transporting pharmaceuticals from the body in the, for example, legs or lungs or etc. So this is many fields that you can apply your knowledge. It's really many fields. So the next part of your question, the radioactive isotopes, including the iodine, it's some sort of it's of course it's a radioactive isotope. It's emit radioactive it emits gamma rays, and we detect the gamma rays, and we can tell what exactly place in human body we detect these isotopes. And when we can can say that in this particular region we have cancer or another diseases, and it's help doctors to identify the place of the cancer and planning the treatment plan. And the third part of the question, can you please repeat the third part of your question? I almost forgot. Repeat please the third part.
So the part of my question is the key underlying mechanism that enables 123I diagnostic isotope to do its functionality, specifically imaging of the thyroid gland. I think, for example, when you're using PET imaging, we should apply radio tracer first.
So I think I understand the question. All radioactive isotopes use as the we can call it contrast material that if we use for example the CT, we scan whole body and we can see special regions in our body. And when we trace the radioisotopes, we can see the current location of these isotopes. It's like a flashing in the CT films. And it's the way to use these isotopes. It's some sort of.
Thank you very much for your answer.
Thank you.
Okay, thank you. Any more question? Come to the front.
Yeah.
Say your name, your university, and the question goes to whom?
Sorry, permission to ask. Sorry to say this, but I'm a civilian. But if I may ask something, am I allowed to ask something as a civilian?
Repeat, please.
I'm not involved in any of the teams. I'm just a civilian in getting involved in this event. May I ask something?
Yeah, of course.
Sure.
Okay, so earlier we said regarding the presentation, it involves one of the presentation involves the material involves explanation regarding reactors and everything, industrial reactors, power reactors, research reactors, and frankly, while we are building reactors everywhere in Indonesia, we seem to forget one thing about the production itself, like the enrichment. Are Indonesia allowed to enrich uranium by themselves, or whether or not they are importing from Russia in the form of uranium-235 and every other material, and if we allowed, what about the byproducts of those enrichments, like the depleted uranium? Because depleted uraniums, while useful in discipline applications like aircraft counterweights and dense materials in general, are also used in military. Are those regulated on the same level as the nuclear weapons, or depleted uranium just counts as a inert material that can be used like tank guns and body armors, or is there any separate regulation regarding the distribution and production of byproducts like depleted uranium? And speaking about the scholarships, one of the measures is mentioned in the presentation earlier is the measure regarding nuclear power plant engineering. What exactly which nuclear power plant type are we talking about exactly? Do we talk about pressurized heavy water reactor, pressurized light water reactor, or which type of nuclear reactors are we specifically learning in those universities, or are we learning about the designs in general for every single nuclear reactor in existence, or are there specifics?
So it's a very common question. Miss Anna, can I ask you to help with Miss Anna? Can I ask to help with the answering this question about the power reactor technologies?
Okay. Okay, I apologize for being anxious. Allow me to reiterate my question. So my first question is regarding, earlier we talked about reactors in one of the presentation. And frankly, while we're building reactors in Indonesia, we also have to talk about the production of the materials used in the reactors itself, especially the enrichment process. In the future, are Indonesia allowed to enrich uranium by themselves, or are they need to import uranium from other countries like Russia? And if they are allowed in the future to enrich uranium by ourselves, how about the byproducts of those enrichments, like depleted uranium? Are those regulated as weapons or civilians? Because depleted uranium, while useful in civilian applications like aircraft counterweights, are also useful in armor-piercing pin-stabilized discarding sabot, the tank count made out of depleted uranium, because it's not radioactive. It's frankly inert material used for defense. Are they regulated as the same level as nuclear weapons, or are they regulated under different regulation, or are they not regulated at all and are considered as just dense material? And second of all, regarding one of the majors involved in the presentation earlier about nuclear power plant engineering, are we learning about the design of nuclear power plant in general, or are we learning about specific types of nuclear reactor like high pressure, pressurized like water and pressurized heavy water reactor, or
Thank you for the question. For the first question, of course, Rosatom, as one of the leading nuclear companies in the world, is producing all the stages of nuclear fuel cycle. So when we cooperate with partner countries, we can supply uranium products, and we of course supply fuel for our types of reactors. So from our side, we do supply all necessary materials and fuel for reactors, which we build by ourselves. If we speak about the development of fuel cycle in Indonesia, it's of course it's regulated by different international conventions and rules, and it's very enrichment of uranium is a very sensitive question, and it's a matter of discussion not between Russia and Indonesia, but with international regulatory and supervisory institutions. And speaking about learning reactor technologies, of course, in the Russian universities, you can get information about different types of reactor technologies, but I think Dr. Vera will speak in more detail about the programs in our universities on this particular subject.
Thank you very much. The question on what technologies you can learn are in Russian universities if you study nuclear in Russia. I can say that within your study, you will learn all technologies, nuclear and related technologies existing in the world, because as our Ms. Vera today presented, there are about 24 universities of Rosatom, and all these universities are focusing on different technologies. So you can learn our small modular reactors technologies, our study program that exists in Nizhny Novgorod University. You can learn our traditional nuclear power plants technologies in our MEFI University, Moscow Nuclear University. So you can learn our nuclear research reactors technologies in Tomsk Polytechnic University. So the thing is that you can learn and you will learn if you study nuclear in Russia, all existing technologies and the thing is that as a part of your study, with the support of Rosatom, all our international students have an opportunity to get a practical internship in Rosatom centers, training centers. So, and of course, during the practical internship, you will get the practice at the facilities that are built with the use of Russian technologies. So, however, you will get the knowledge on all existing technologies in the world.
Thank you for answering my question.
Okay, thank you. One last question. Come here. So your name, university, and the question goes to whom?
Yes. My name is Phil. I study Polytechnic Nuclear. So my question is for the panelists from Russia. So from Rosatom perspective, or any of the panelists, does I'll repeat the question. From Rosatom perspective, or any of the panelists from Russia perspective, what are the most important things that ensure long-term success when collaborating with countries like Indonesia that are just starting out? What is the most important thing that ensure long-term success with collaborating with countries that are just starting out with nuclear technologies like Indonesia?
So thank you very much for your question. I would say from my perspective, from my point of view, I suppose that there are two most important things when you start the cooperation with our partner countries. First, this is public acceptance of the nuclear technology. People need to understand that it's safe, green, and we do pretty much about public awareness and public acceptance, providing more and more information about nuclear technology, their applications in medicine, agriculture, energy, and other fields, answering all the questions to the people, to the simple people, that it's absolutely safe to live near the reactor, to work at the reactor. And the other very important thing I've told you already is people, because highly professional people is the key element of the success of any nuclear program at any stage of its realization, starting from decision making about having a nuclear power plant or the center of nuclear technology, to its constructing, maintenance, operating, and the backend and the decommissioning. So that is why we understand that the cooperation in the field of human resources development, education development is very important too. So this is from my perspective. I think that my colleagues from Rosatom Indonesia could also add something to my answer.
Here. I also have a question for the people from BRIN. Kalau boleh pakai bahasa Indonesia. Dengan berbagai proposal yang baru datang dari beberapa negara, apa yang menjadi poin-poin pertimbangan memilih partner kerjasama yang paling besar? Apa yang menjadi poin-poin pertimbangan memilih partner kerjasama dalam nuklir yang paling besar? Dengan luar negeri, Mas.
Ya.
Jadi kalau BRIN itu biasanya kita melihat dari topik prioritas riset yang ada di BRIN ya. Jadi misalnya apa namanya seperti contohnya visual pendidikan targeted itu kan ada 4 bidang prioritas. Yang pertama adalah utilization. Yang kedua nuklir, gas, space, tempat, diksi, dan maritim. Nah, itu hal yang jadi penting gitu untuk riset kita. Kalau kita nggak bekerja sama dengan universitas luar negeri yang memang lebih advance ya, kita akan sulit mengejar ketertinggalan. Itu yang menjadi dasar kerjasama dengan Masnya nanya apa yang jadi dasar BRIN itu ketika memilih mitra luar negeri.
Okay. Should I answer in English or Indonesia? Indonesia is better. Oke. Baik. Salah satu pertimbangan BRIN mencari kolaborator dengan perguruan tinggi lain tentunya adalah basic dari kerjasama yang telah dibangun sebelumnya. Ya. Jadi beberapa perguruan tinggi mitra kami di luar negeri itu memang sudah punya kerjasama yang dibangun sebelumnya. Dan itu kita perkuat. Kenapa? Umumnya sebelumnya itu ketika kita ada program untuk S2, S3, itu cuma 1-2 orang yang berangkat. Ya kan? Padahal kita butuh bagaimana bisa mengakselerasi secepat mungkin banyak anak-anak muda ini, talenta muda ini terekspos. Makanya kita bikin program yang namanya konsepnya itu adalah sistem cohort, grouping. Kayak begitu. Nah, jadi dalam kesempatan yang sama, kita bisa mengirim sekaligus beberapa orang untuk studi ke luar negeri. Nah, tentunya ke depan dengan mengenalkan program tersebut, kita berharap kampus-kampus lain juga akan semakin banyak berminat untuk bisa menerima program-program kita, terutama dalam pengembangan talenta dengan kampus-kampus mereka. Begitu. Nah, tentunya semakin banyak yang kolega kita yang pernah studi di luar negeri atau segala macam, itu bisa memberikan masukan ke kita, kemungkinan untuk bisa menguatkan kerjasama tersebut, dan kita dorong, kita support dengan sekaligus untuk pengembangan kompetensi baik sekolah, S2, S3 maupun kolaborasi risetnya. Itu sebenarnya esensinya. Ya. Cukup? Cukup. Oke.
Terima kasih. Okay, thank you. Because of time, I think I have to finish this session. But before I close this session, I need to ask our panelists to provide closing remarks to motivate our younger brother and sisters here to go for higher study on nuclear field, especially in Russia, starting from Mikhail. What your closing remark to motivate our students here to go for nuclear study in Russia?
So at the end of the session, I want to say that, first of all, I wish the good luck for all participants of the hackathon. And I hope that in my presentation, all of you find something new and find something that push you to go through all steps of education and finally find you in the certain area of the science of nuclear science. Thank you very much.
Dear colleagues, dear students, so let me first of all thank you, our colleagues from BRIN, for giving this opportunity to talk to you and for organizing this wonderful event. And I would like to wish all of the students good luck during the hackathon. Be brave. Don't be afraid of your unusual ideas. It will be really helpful if you come out with some new ideas. And actually, we are looking forward to seeing all of you in Russia. You're welcome. So, and if you have any questions, we will keep in touch and will be open to contact you and to reply any question from you. Good luck. Thank you.
Now, your turn, Naba.
Oh yeah. What can I say? I just really hope that what I've shared today from my experience in studying in Russia and being part of the Russian Nuclear Education Ambassadors from Rosatom can give you a clearer pictures and maybe even inspire you to explore the Russian education even itself, so by yourself. So if you're interested in studying in Russia or learning more anything about studying especially in nuclear industry, feel free to reach out. Feel free to reach out or stay tuned for the next present for the feel free to reach out and just stay tuned from the next event. So once again, thank you so much, BRIN and Global HACKATOM Indonesia, for having me, and good luck to all of you, the participants that's going to have the competition. And it's an honor to be part of this initiative that supports and empowers the next generation for the nuclear talents.
Thank
So
you.
yeah, it was a pleasure to be
Thank you,
here.
Naba. The
Thank
last,
you.
but for not the least, from our Deputy Chairman, what is your recommendation to motivate our students to go for nuclear field?
Baik, saya kira kalau kita flashback bahwa belajar tentang nuklir itu bukanlah sesuatu hal yang terjadi sekarang-sekarang. Tadi udah kita gambarkan sejak era Soekarno itu sudah mulai digalakkan, sudah mulai dikenalkan, ya. Dan apapun itu, ya, nuklir dan antariksa adalah dua pengetahuan, dua teknologi yang mesti harus dapat kita kuasai. Kenapa? Disitulah kita bisa banyak belajar tentang bagaimana advance teknologi, ya, kalau kita masuk ke bidang kenukliran maupun ke antariksa. Nah, dan tentunya BRIN sudah memberikan semua programnya dan fokus di kedua bidang tersebut. Jadi saya kira tinggal kepada teman-teman mahasiswa untuk mengambil challenge tersebut atau tidak. Menjadi bagian dari generasi nuklir kita masa depan atau tidak. Kenapa? Kita membutuhkan talenta-talenta unggul di bidang nuklir, bidang antariksa ke depannya, dan itu harus dimulai dari sekarang. Jadi kesempatan itu ada di tangan kalian. Terima kasih.
Yeah, it's time to close the panel session. Let's give big thank you to all panelists. Thank you. Back to MC dan pada adik-adik semua, selamat mempersiapkan diri untuk presentasi besok. Good luck to you.
Thank you so much, Prof. Julwan. And thank you so much for all of the speakers. That was a very insightful session. And please kindly give a round of applause again for our speakers. Okay, and please for all the speakers, I'm sorry, can you please back to the stage? Sorry, for all the speakers, can you please back to the stage? We will have a photo session. I also invite Dr. Vera, Mrs. Anna, Bu Ajeng. Ya, terima kasih. Mohon sebentar untuk Pak Anhar, kami undang juga untuk bisa bergabung di atas panggung. Thank you so much. Pak Edi Giri, Mrs. Anna, and Dr. Vera, please remain on the stage. The others can be back to the stage. We will have a standing souvenir session from BRIN to the Committee of Global HACKATOM Indonesia, to the Committee of Global HACKATOM Russia. The standing souvenir from BRIN will be represented by Bapak Edi Giri to Dr. Vera and Mrs. Anna. Thank you. Thank you. All the speakers and the guests can be back to the seat. Well, ladies and gentlemen, I hope you all are enjoying this event. It's a very long, but I really hope that you will have a very good insight and a very good opportunity to get a very much more information for you to study in Russia, study nuclear, or get a very beneficial programs from BRIN. Now, that is all actually for this morning agenda. And we would like to express our gratitude to for your participation today. Thank you so much for joining us today. And on behalf of the organizer, and me personally, I would like to apologize if there is any inconvenience during this event. And as this morning agenda is part of the competition of Global HACKATOM Indonesia 2025, there will be agenda later after lunch break for the finalists. So be back here at 1 p.m. And well, that's the information for the finalists and for all of the participants. I again thank you so much for joining us today. And this is not a goodbye. We look forward to see you again in the next event. Good afternoon.
Baik, Bapak Ibu, adik-adik semua,